Kemmeter, so Jean-François de Kemmeter. I hope I'm pronouncing it the right way.
Yes, of course, perfect.
From the University of Namur, and the floor is yours. Go ahead. Thank you.
Thank you very much. Can you see my screen and also the cursor moving? Yes. Okay, so first of all, I would like to thank the organizers for giving me the opportunity to participate in this workshop in memory of Professor Nicholis. So this talk will be devoted to some dynamical aspects of a particular class of non-linear random walks occurring on top of networks.
Yes, just one thing. Now your screen is not showing the presentation. It was a few seconds ago, but somehow it disappeared.
Yes, I will try and repeat once again. Can you see it now?
Yes.
Okay, so perfect. So as I said, so this talk is devoted to a particular class of stochastic processes taking place on top of networks. And so this is joint work with Professor Timoteo Caletti, my thesis supervisor from University of Namur, as well as with Malbor Aslani, Associate Professor at University College of Dublin. Here is the outline of the presentation. I will start with a brief recap about the concept of linear random walk on top of complex networks. Then I will define the class of nonlinear random walk we have considered in our work, and we will see that it leads to the emergence of functional communities. Then in the last part of the presentation, I will consider the special case of regular networks, namely lattices, and we will see that also in these networks, we can have symmetry breaking from a homogeneous state to an inhomogeneous one. So let me start with the first part of the presentation devoted to this linear random walks. Throughout this presentation, I will consider undirected and unweighted connected networks like the one you can see here on the left. And so this linear random walk describes the motion of an agent which hops from one node to one of its neighbors with equal probability. And so the structure of this network is encoded through this adjacency matrix whose ij element is 1 if and only if there is a link between node I and node j and 0 otherwise. The dynamics can be described by this first order differential equation where the vector rho has its components giving the probability to observe the random walker at some node and at some time. And this matrix here is the random walk Laplacian, which is expressed as follows. And here D is the diagonal matrix of the connectivities of the nodes. And in the long run, the probability to find a random walker at some node is proportional to the degree of this node, and this independently of the initial conditions. However, an unbiased random walk cannot account for complex interactions among individuals. For example, if you consider the population dynamics on top of a metapopulation network like this one, then you have to take into account the limiting carrying capacities of the nodes, namely the fact that nodes can host at most a given number of agents. This means that an agent cannot hop to a fully occupied node. At the same time, we would also like to take into account the social behavior of agents, namely the fact that agents tend to prefer go to nodes where there are already sufficiently enough individuals. And so this dynamics will be described by some biased random walk, where the bias now will not be encoded through a topological aspect of the network, but instead the bias will depend on some dynamical property, which is the density of the nodes. The system can be described by the following vector, whose components give the number of agents at a given time and at some node. And the probability of observing this state is governed by this master equation. The first term here is a gain term thanks to a transition from a state n prime to state n, while here the second term is a loss term due to a transition from state n to another state n prime. And now it remains to give an explicit expression for these transition probabilities, taking into account both the limiting carrying capacities of the nodes, but also this social behavior. So coming back to the same picture as before, the transition rate corresponding to the hop of an agent from node I to node J will be expressed as follows. So this is a product of two independent terms. The first one gives the willingness of an agent to leave a node. And in the following, we'll suppose that this function f is the identity function. So this term is exactly the same as the one for a linear random walk. But here we have this second term, which depends on the density of the target node. So this is where the bias will be introduced. So this function g is expressed as follows. So the larger the density in the target node, the more individuals this node will attract. But at the same time, we have to take into account this limiting space by here having this factor. Here, I suppose that all the nodes have the same limiting carrying capacities, which is given by this maximal number of agents n. And we can directly see from these equations that the transition rate to an empty node or a fully occupied node is forbidden. This model is an extension of the following two papers, and the novelty here is this term, and this term will drive new dynamics, which is quite complex, as we'll see in a few minutes. If we take now the mean field equation, then we obtain a system of differential equations which are nonlinear, which are coupled to each other, and the time evolution of the density inside a node will be given by this right-hand side. So this is the sum of two terms. One is the outgoing flux from node I to its neighbors, while here the second term is the ingoing flux towards node I. And this system can be rewritten in a convenient way using the random walk Laplacian. And we can indeed check that the total mass is conserved. The function g here takes the following expression, and here is a sketch of this function. So you see that it's positive in the interval 0, 1, and it cancels at the bounds of this interval. Now let us consider the special case where the logistic function is taken as for the function g. So in this case, the system of differential equations takes this form. And it is important to notice that we have here this prefactor, which allows a priori the existence of empty nodes in the steady states, namely nodes whose stationary densities is exactly 0. And indeed, this is what we can observe in this right picture. So the network is the same as the one I showed you in the first or second slide. I start with the following homogeneous state. And here I represented the stationary densities using this color map. And interestingly, we can see that in the steady state, we have the emergence of some empty nodes that are represented in white here. And the mass accumulates in some nodes that are organized into clusters. So these clusters can be seen as some meta communities or functional communities. And they are isolated from each other. They cannot interact due to these empty nodes that act as boundary. So in other words, this dynamical process can break the functional connectivity of the network. The lower this node, this mean density, the larger the number of empty nodes. And on the other hand, if you consider a crowded network, then there will be no empty nodes. And in this case, you can explicitly find the stationary density, which are given by this expression. And in this expression, the constant C depends both on the total mass M and also on the structure of the network. Let us now turn our attention to the case of lattices. For lattices, the system of differential equations takes this form, and you see that the homogeneous state is always a fixed point of the system. But this is not the only possibility. You can have other fixed point, which raises the question of the stability of the homogeneous state. To answer such a question, we compute the Jacobian matrix of the system evaluated at this fixed point. And this Jacobian is expressed as the Laplacian matrix times a prefactor. And this prefactor depends on the average node density and also on the function g. From the properties of the random walk Laplacian, it follows that the homogeneous state is stable as soon as this condition is fulfilled. So here on the right is an example of lattice, so for example, a square lattice with periodic boundary conditions. So if we come back to this condition of stability, what we see is that if we take the logistic function, then the homogeneous state is always stable. But if we consider a larger class of functions, then the conditions of stability becomes the following. And you see that in particular, if you take, for example, a equal to 2, so you take the function g to be the square of the logistic function, then the homogeneous state becomes unstable as soon as the mean density is lower than 1/3. If the homogeneous state is unstable, then the question is, what does the steady state look like? And here I'm going to show you some numerical analysis we performed with this particular function g. The system was initialized with the following set of initial conditions. So we perturb the homogeneous state with random numbers. The size of the perturbation was controlled through this parameter. And the initial conditions were renormalized in such a way that the total mass is preserved. And on the right here, you can see the time evolution of the densities for a network made of 20 nodes with this mean density and with the following size of the perturbation. And you see that indeed there is a symmetry breaking because the homogeneous state turns out to be unstable. In the asymptotics, we find some empty nodes, but also some filled nodes which have distinct densities. Here you can also see this symmetry breaking. In this case, we consider the special case where the perturbation is applied to one specific node, which is indicated here by the black arrow. And you see that depending on the value of this parameter beta, which is the total mass divided by the number of nodes, you see the emergence of some empty nodes. So as beta gets lower, the number of empty nodes increases. And you can also see that this increase of empty nodes happens quite abruptly. This is indeed confirmed in this picture, which was obtained again for a ring network, but this time with 50 nodes. Here we represented the number of empty nodes as a function of beta. And you see that the fraction of empty nodes evolves as a quantized manner. And here, we have a phase transition here. And this picture suggests that we have a polar behavior close to this particular value of 1/3. And this can be confirmed using some numerical analysis. In this picture, we took a network made of 100 nodes. We initialized the system again by perturbing slightly the homogeneous state. And we reported fraction of empty nodes as a function of the distance from this particular value 1/3. So this is a log scale, and we indeed see that the fraction of empty nodes follow a polar behavior, and this the exponent is predicted to be around 1/4. Such symmetry breaking can also be observed in lattices with larger connectivities. And on this right picture here, I represented the critical exponents governing here this polar behavior as a function of the connectivity. This brings me to the end of the talk, and I would like here to summarize the main points. So first, we have introduced a new class of nonlinear stochastic processes on top of networks that take into account both the limiting carrying capacities of the nodes as well as the social behavior of individuals. And interestingly, we observed the emergence of some functional communities or meta-communities. And also in the case of lattices, we have a symmetry breaking from homogeneous state to an inhomogeneous one, depending on the way we model the nonlinear interactions. And such results can potentially shed light on the existence of volcanic in ecology, but also it can be of interest to understand the formation of urban prairies. So thank you very much for your attention, and if you have any question, I'll be pleased to answer them.
Thank you. And so are there questions? I have one.
Yes.
So at some point you define the mean field solution for the rho.
Yes.
And I think in that definition you have the mean of 1 over k. You can go back to the slide.
Yes. So maybe this slide or another?
No, just the mean field solution, the homogeneous mean field solution.
This may be
this one.
Yeah,
so k is the is sort of the distribution of connectivity.
Yes,
How can you be sure that this mean exists? What sort of distribution are you allowed to take or not take?
Well, I would say that when the topology of the network is fixed, then we can compute exactly this average over 1 over the degree of the node. And so there is no ambiguity since we consider a connected network.
It's just that for some distributions, there is no mean, especially for the inverse of.
Yes, I understand now your point. So indeed, we have to consider finite networks with a limited number of nodes, or to be sure that indeed we have some random networks such that in the thermodynamic limit where the number of nodes becomes infinite, indeed this quantity is finite. But here in this simulation, we always consider finite networks, so there is no problem regarding the existence of these points. Yes.
Good.
Thank you.
Is there any other question? I think everyone is hungry. So if there is no other question, let's thank again our last guest for this morning session. And remember that we will reconvene at 1:30 for a session on nonlinear dynamics and beyond. And till then, take care and have a nice lunch.